In this video, we're going to go ahead and rapid fire 3 alternating series, because again, I would argue that the alternating series test is actually quite smooth in its conclusionary statements. So the first one we're going to do here is -1 to the power of k plus 1 divided by k squared. So this is technically like an alternating p series, just like we worked with the alternating harmonic series. So remember, the first 2 things we have to prove is, number 1, that my a sub k equals, in this case, 1 over k squared. Again, I'm pulling the negative piece away. In this case, this is the power of k plus 1. Again, that k plus 1 could be k plus 5, it could be k plus 3, it could be just k. It's still going to be the negative alternating piece, which we're going to take away, and everything that's left over, in this case 1 over k squared, is my magnitude terms. So we're going to start with this piece and just make sure that, first off, this thing is going to be always non-increasing. How do we know that it's always going to be non-increasing? Well, if I go ahead and change it to k to the -2 and I take that derivative ak prime, I'm going to go ahead and get -2 k to the -3. In this case, I'm going to have -2 divided by k to the power of 3. And because we're always using k equals 1 positive terms, the bottom piece is always positive, the top piece is always negative. So I can conclude that a sub k is always non-increasing. Okay, so that's the first quality. The second quality we have to prove, remember, is taking the limit as k goes to infinity of my a sub k, so 1 over k squared, which inherently is right there equal to 0, because as k goes to infinity, the bottom piece gets larger, and 1 over something getting larger goes to 0. And there's my second detail concluded. So, by the alternating series test, the series I was given, and again, we should be really clear about how we write it, the series of -1 to the power of k plus 1 over k squared is then convergent. So that's the first example. And again, this is why I'm saying we're going to rapid fire these, because I did that problem in less than 2 minutes. So we're going to keep working through these. The concept is you just got to make sure that you tear apart the -1 from the rest of the series. That k plus 1 is the exponent of that -1, so that's a separate piece. And this is my so-called a sub k. Now, for this one, my first detail to start off with is a sub k, again, is equal to k plus 1 all over k. And I'm supposed to take the derivative of this thing. Well, I'm going to go ahead and hold off on taking the derivative of this thing. We can work through it. The same thing is going to be basically 1 over k. 1 plus 1 over k if I simplify it. This piece is just 1. This term becomes the same derivative I took with the alternating harmonic series, the -1 over k squared. So again, I might as well just go ahead and do it. This is going to be, the derivative of this is 1 minus 1 over k squared when we take that derivative. And with that being the case, this thing is then, again, non-increasing, and we've got that detail solidified. Number 2 is, again, for us to go ahead and prove that the limit as k goes to infinity of this thing, 1 plus 1 over k. Again, all I did was distribute that division to simplify it to this, and then I get to here. As k goes to infinity, this thing equals to 1. Well, then we don't have the necessary conclusionary statements. And actually, more importantly, it's important to note that if I were to take the limit as k goes to infinity of this thing right here, the limit as k goes to infinity of this overall thing, we will be able to conclude that this thing bounces back and forth. It equals to either -1 or +1. And when I say that, I don't mean that it actually equals to it. I mean that that's what it's approaching. It's approaching a value such that it bounces back and forth between -1 and +1. And by limit standards, this limit doesn't exist. And remember that the divergence test specifically states that the limit must equal to 0. The limit must equal to not 0, otherwise the series itself is going to be divergent. So because this thing does not equal to 0, because it equals to something other than 0, we can conclude that this thing overall, the series -1 to k plus 1 of k plus 1 over k, is divergent by the div test. So again, it's kind of smooth that in this alternating series test, one of the statements basically ends up working with a div test in its core, which helps us make the conclusion that, well, yeah, it is a divergent series, specifically because of the div test, the way it works, and because of the alternating series test with the way it has it. So now let's go ahead and look at this last example right here. This last example might actually look a little bit familiar. We've done stuff with natural log of k over k before, but we're going to go ahead and treat this just like it's an alternating series one more time. I'm going to go ahead and have a sub k equals 2. Now notice that negative 1 to the power of just k this time. Again, that doesn't change how we behave or how we treat this. That negative 1 to the power of some form of k is going to be moved off to the side, and I'm going to have my a sub k be natural log of k over k. So, with this, let us go ahead and take the derivative of this function and see what we can conclude. So a sub k prime is going to be equal to, well, this is going to get a little tricky because we're going to have to apply either the product rule by moving this k to the power or to the top with a power of negative 1, or we're going to have to use the quotient rule. In this case, I'm going to go ahead and just straight up use the quotient rule because I think it's going to be more efficient. So I'm going to take the derivative of the first function, which is natural log of k, so the natural log of k goes to 1 over k, multiplied by the second function unchanged, minus the derivative of the second function is 1 times the first function unchanged. This is all divided by the second function squared, or the denominator squared. So in this case, I'm going to have 1 minus the natural log of k all over k squared. And if you watch the video on working through the more complicated series natural log of k over k, we do end up concluding that this term right here is always going to be smaller than this term right here after a certain point. So the idea is that, yeah, sure, this is starting at k equals 2. Actually, that works out well, because if we plug k equals 2 into here, natural log of 2 ends up being a value larger than 1. So what if we started at 1? If we started at 1, this series might not have been satisfying for the a sub k derivative. So this thing is always negative. Again, it's always going to be negative simply because we're starting at k equals 2. So that satisfies the first detail. We do know that this thing is always, again, non-increasing. And we really should be making this statement every single time. I've just gotten lazy about writing it, but I should be making that statement after that second detail. Now, number 2. Number 2 is the limit as k goes to infinity has to be equal to 0. Well, natural log of k over k, in this case, again, infinity on top, infinity on the bottom. We've done this before in a previous video where I use L'Hopital's rule. I get the limit as k goes to infinity of the top goes to 1 over k, and the bottom goes to 1. This thing then ends up going to 0. And sure enough, by the alternating series test, the series negative 1 to the power of k times the natural log of k over k will converge. Again, by the alternating series test. So again, there's your rapid fire 3 specific examples that are all slightly different, where one of them will conclude divergency, but the other two will conclude convergency, specifically based on just checking those two qualities. Number 1, is it always non-increasing in its terms? And number 2, does its limit equal to 0?